Good morning, class. So, the topic of discussion today is symmetry operation. What we will see in this lecture, what are symmetry operation, what are its kind, where they apply on a point, about a line, about a plane, okay, and their combination, okay. So, class, firstly we see we are discussing the crystal structures. Crystal structures. Crystal structures. In very first lecture, we have discussed what are the properties of crystal structure. The very basic fundamental first property about crystal was periodicity. Okay, and then definite arrangement of constituent particles, and then sharp melting point. Okay, definite arrangement, definite kind of particles are collaborate with each other to form crystal structure. So the bond strength, that is bond strength, that was fixed. That's why the melting point was sharp. Okay, class, melting point was sharp because all bonds are equally strong. All bonds are equally strong. We have done all these things when we compared the crystalline solids with amorphous solids. Okay, class, I am writing here all bonds. If you see it, this is for ideal crystal, mean to say where particular kind of bonds are there, but you know that there is nothing in the world like which is ideal. Okay, so some imperfections are always present in the crystal as well. So if the bonds, if I assume it to be true crystal, mean to say all bonds are made up of same kind of particles, the arrangement is definite, okay, and bond strength that is same, then the melting point will be sharp. Okay, so don't get confused with sharp and fixed, it is same thing. Okay, class, so here come to the topic of the day, that is symmetry operation. Okay, you see everything in crystal structure start with this basic property, that is periodicity, definite arrangement. So here also the thing is same. This is periodic, mean to say if you walk, if you rotate, if you take mirror image about a plane, okay, and if you take rotation and then reflection, I am combining two things here, one is rotation and then reflection. So if you apply any kind of operation, then the crystal remains the same because of this periodicity and definite arrangement. So what I want to say, one more property which is very important and which will help you to justify the symmetry operation, that is long range order. It is very important. So here I am writing long range order. So this combination is very important. First one, the arrangement is definite, then the arrangement is periodic, and then it is of long range. Okay, class, so this all combination gives rise to symmetry operation. If you do any kind of if you apply any kind of operation, then the crystal repeat itself. Okay class, so this leads to symmetry operation. So now come to the topic. The topic is symmetry operation. So here I am starting with symmetry operation. Symmetry operation, you see, operation is a kind of action. Operation is a kind of action, okay, which is applied on symmetry, and symmetry is in case of crystal. Okay class, so symmetry operation, it is an action which is applied on the crystal structure, which leaves the crystal structure itself. Okay, or you can say which leaves an action which leave the crystal structure unchanged, invariant. Okay, then that operation is symmetry operation. Mean to say, an operation which do not destroy the symmetry of the crystal structure, that operation is symmetry operation. So you can understand it and you can write the definition in your own way. All things are correct. So this is an action or operation, you can simply say an action which leave the system crystal structure unchanged or invariant. Okay, or I can write an action which don't simply disturb the symmetric arrangement. Symmetric arrangement of constituent particle in the crystal. So class, I have told you the same definition in different ways, all are correct. You can write of your choice. Then come to rotation about an axis. These are the type of symmetric operation. So first one is rotation about an axis. We will see it. Stop. So now the first kind of symmetry operation, that is rotation about an axis, passing through a lattice point, passing through a point. So class, in this what we will do, suppose simply we have such kind of arrangement and this crystal structure, it is 2D, it is in 2 dimension. Okay class, and if I take any point, you can take a point of your choice, you can take the point to be here or you can take the point to be here, and if you rotate it about an axis which is perpendicular to the plane of the crystal. So here we are talking of 2D, and if it is a crystal structure, then particles are arranged in definite fashion and the order of arrangement is long. So for simplicity, I am showing only 4 particles and rest of the particles you are to keep in your mind. Okay class, so here we have this is the point and this is the axis. I am taking the chalk which is perpendicular to the plane of the board to be the axis, and I rotate this crystal structure. Then what will happen, the crystal structure for some particular angles will repeat itself. Okay, I am saying that in the very first in the definition I told you that an operation, an action which leave the symmetry of the crystal unchanged, okay, that is symmetry operation. Okay class, mean to say this is some definite kind of operation, it is not arbitrary. Why? Because arrangement of particle is definite. Mean to say class, you see this particle, if I rotate this by 30 degree, say 30 degree. So this is the direction in which particles are arranged, okay, and about this axis which is perpendicular to the plane, I rotate it by 30 degree. Then you see this particle will come here, this particle will come here, and then you will see the direction has changed. Okay class, okay. See what was the initial direction of arrangement? The initial direction of arrangement was this. This is the direction. This is the direction. Okay, but after 30 degree rotation, you see the arrangement of particles become in this direction. Okay class, it means the symmetry has changed. Okay, so in this case, this operation which rotate the crystal, such type of crystal by 30 degree, that is not acceptable because it has changed the symmetry. But see, if I change this type of crystal by 90 degree, then you will see this particle will come here. This is the position of the particle now, okay, and this particle will go here. This particle will turn and come here. Okay class, now see, this particle has come here and this particle has come here, okay, and this particle will go there. This particle will go there. Now see, before rotation, this particle was at a distance A, and after a rotation of 90 degree, this particle is again at a distance of A, and this particle, let it is A, now it has come at place of A dash. Now this particle, let it is B, it has come at the place of B dash. Now after rotation you will see this is again at a distance, okay, let's see it in deep. Let the arrangement of particles is at a distance of A in both direction, okay. So this distance is A, here this distance is A, this distance is root 2A, okay, and after rotation this distance is again root 2A, okay. So if this particle goes here at the position of, let this is C particle, and C particle go at the position of C dash after rotation, then before rotation it was at a distance A and now it is again at a distance of A. So I can say that if this kind of arrangement of particles is present, this is the kind of arrangement where particles are present, and if I rotate this by 90 degree in clockwise or anti-clockwise direction, then the symmetry of the crystal structure remains the same. It will be same as it was before operation, okay class. So this is what rotation about an axis passing through a point, okay. So if you define it, this is a symmetric operation in which if the crystal is rotated about an axis passing through a lattice point perpendicular to its plane, then it leaves the whole crystal structure same, invariant, okay class. So now come to another point, that is reflection in a plane. So second point here is reflection. You have a reflection in a plane. So class, the first point was in reflection in a plane. So if you have a kind of arrangement, let particles, I am taking the same crystal structure because it is very simple to understand. So if this is the kind of arrangement, particles are arranged in 2D, okay, I am taking that direction, okay, and particles are arranged in this direction at the same distance, let the distance be A, okay class. So if you see, another particle will be present at a distance A. Why? Because it is long range periodic arrangement. So this distance is A, it is A, it is A, So one particle is present here, and if you see along this direction, another particle will be at a distance a, next particle will be at a distance a. Okay class. So if you see in this case, if you take a plane which is passing through this line and perpendicular to the 2D plane, I put a mirror here. Let this is the mirror, okay, which is passing at a distance of a by 2 from this lattice point and a by 2 from this lattice point. Then you will see these points on the left hand side, will become mirror image of the lattice points which are present on the right hand side. So in this way, this plane is this plane is plane of reflection which repeat the crystal itself. Okay class. So in this way you can understand the reflection in a plane of crystal structure. Now we have another operation, that is inversion about a point. So class, you see the previous operation reflection, it is about a plane, and before this it was about an axis, okay, about a plane. Okay, now come to the next point, that is inversion. This is about a point. So what happens in this case, come here, we have the third point, that is inversion. Now see, in case of inversion, what will happen, there will be a rotation. In actual, first of all, it is about a point, and you can assume it to be a compound operation. It is a compound operation, okay, compound word is used, so it is a combination. So here this is basically a combination of operation, and the combination of rotation by 180 degree, and then plus, I will say, a reflection. Okay class. So this is a compound operation. Okay class. Now we will see this compound operation step by step. Okay, and this operation about a point, it is in 3D. How it is in 3D, you will see here. Suppose we have arrangement of particles, a kind of arrangement. This is a hypothetical example. Okay class, this is the point about which we are to apply the inversion operation. Okay, and particles are present here. Let me use different colors. This is a particle, okay class, and this is another particle, okay, and we have then another particle here. Okay, so here see, let this point to be O, this is O point, and this is A atom, B atom, and C atom. Now what we are to do, we will take mirror image of it. This is the dotted line which is perpendicular to this dotted line, and this is the mirror. So why we are making use of the mirror? Because the inversion is combination of reflection and rotation. So see, in this case, the point A is at this much distance, it will be here at this much distance. This is, I write it A dash. Okay class, and this is B, this is B, I am writing it B dash, and then we have C. Then you have C, it is at this much distance. This is C dash. Okay class. Now what you will do? You have taken one operation, that is reflection. The positions are shown in this reflection operation. Now the operation is taken along this plane y dash, which is perpendicular to the plane of the paper. Okay, if you put a mirror is a two-dimensional surface here perpendicular to the plane of the board, and take the images, it will be like this. Now this is one operation, reflection. Now we will rotate it by 180 degree. Okay, so what will be the rotational axis? Now the rotational axis will be this one. This one will be the rotational axis. Okay, so if you rotate it by 180 degree, I am to rotate it by 180 degree. Okay, so this is the second step. In the second step, I will rotate it this is the axis. Okay, and if I rotate it by 180 degree, then you will see what will be the change in these positions. Okay class, so we are applying operation on this arrangement. So the arrangement was A and B, this is B, and here the particle was C. Now this is the initial stage, initial position, initial arrangement, it is same. Okay, now this is intermediate stage, this is first stage, this is first stage, and after this operation you get this stage. Now if you rotate it by 180 degree, then what will be the change in this thing? This C, if you rotate it like this, C dash will go at the position of A dash, and A dash will come at the position of C dash, and B dash will be at the same position. So finally you will get the C will come here, C will come here, and A will be below it. Okay, and B dash, it is same here. So class, here you can see what kind of operation it is. It is about a point, the point is in the middle. Here it is O point, and the position of C is at this position. You can see this thing and this arrangement. So here you can see this is how the inversion operation leave the arrangement of the particle unchanged. So this is inversion operation. It is combination of reflection and rotation. Okay class, so if you see in the book, it is given like this. A line is here, another line is here, and then this is the same thing. This intermediate position is not shown. So this is the third stage and this one is the first stage. Okay, and the arrangement of particles is same in the initial and the final stage. So this is inversion operation, which is combination of reflection and rotation. It is operated in 3D. Thank you class. Class, one more operation is there, that is translation symmetry operation, and you will see how it is different from the rest of the operations. See here, translation last operation, that is D. We have discussed this. We will discuss this compound operation, which is combination of the two. Translation translation symmetry operation. So it is nothing but simply translation operation. Okay, so class, you know translation vector T, this is given by n1 the primitive vector A plus n2 vector B and n3 vector C. Okay, and this translation vector will connect any 2 point. So let we have a lattice point which is represented by a vector R, and another lattice point at this much distance, and let it is given by a vector R dash. Then to join these two lattice points, you will make use of translation vector. This is translation vector. So here you can see how the translation vector connect the two lattice points. Let this is x and y, and one more dimension you have here, that is z. So here you will see vector r dash, this is equal to vector r plus vector t. You can see in crystal the arrangement of particles is definite and periodic long range. So these are not the only points present in the crystal. The particles are also present in its surrounding. So if you want to move from this point to some another point, then you will make use of this translation. And due to periodicity, definite arrangement, long range order, the surrounding of the particle remain unchanged. Mean to say, suppose here you have a particle and particles are present like this here. Let this is the position. So here you can see this is the arrangement in the surrounding of particle A. Okay, if you make use of this translation vector and you move to the another point, let this point is B, the same kind of arrangement you will obtain in the surrounding of B. So here also the arrangement of particles will be like this. A particle will be here, one particle will be in this direction and another will be here. So you can see the surrounding of A and surrounding of B, that is same. So translation vector is applied between two lattice points. Okay, so this is one of the difference between translation symmetry operation and rest of the operation. Rest of the operation were applicable either about a plane, about a line, or about an axis passing through a lattice point, and this translation vector is in between two lattice points. So thank you class. Now okay, one more operation is compound operation. Compound operation is basically a combination of different operations. So one is glide operation and another is screw operation. These are very simple. You can see these from your book. Okay, one is screw. You know that if you rotate a screw, then what happens? You make use of screwdriver, you apply torque, and what happens? The screw rotate and move along the axis of rotation. So two operations are happening simultaneously. One is rotation and another is translation. So this is screw, and this is combination of reflection and translation. You can see it from your book. So thank you class for watching this lecture on symmetry operation. Thank you class.